Good morning everyone. My name is Prashanth. I am from second year BTech from CSCC. Today we are going to discuss about the distributed averaging with random graphs and noises. Now, let's start with the abstract. We consider a discrete time distributed averaging algorithm over a multi-agent networks with measurement noises and time varying random graphs. Each agent updates its state by a weighted sum of pairwise state differences between its neighbors and itself, with both additive and multiplicative measurements. The network structure is modeled by a sequence of time varying random disk graphs, which may be spatially and temporally dependent. By stochastic Lyapunov method and the combination of algebraic graph theory and martingale convergence theory, we obtain sufficient conditions. For stochastic approximation type algorithms to achieve mean square and almost sure average consensus. We prove that all states of agents converge to a common random variable whose mathematical expression is, is the average of initial values in mean square and almost surely if the sequence of disk graphs is conditionally balanced and uniformly of the limit random variable, that is the mean square steady state error for stochastic average consensus is given by quantitatively related to the weights, the algorithm gain and the energy level of the noises. Now, introduction. In real networked systems, there exist various kinds of uncertain factors such as channel noises, channel fading, random link failures, and recreation. In recent years, stochastic multi-agent networks have attracted great attention from scholars in various fields and become an active interdisciplinary research subject. For scholastic multi-agent networks, distributed averaging is one of the most fundamental problems and has range of and has wide range of fundamental problems such as distributed computation, distributed filtering, information fusion over wireless sensor networks, uh, and load balancing and optimization, etc. Measurement or communication noises affect not only the decision making of each individual agent but also the overall performance of the whole system. Generally, measurement of communication noises are divided into two categories: additive and multiplicative noises. Additive noise corrupts signals in the form of superposition, regardless of its coupling with signals. For example, the effects of coherent fading in imaging radar systems can be modeled by multiplicative noises. Can model multiplicative noises for distributed averaging with additive measurement. Now, distributed averaging with random network graphs and noises is a technique used in distributed computing. It involves a network of nodes that collaborate to compute the average of set of values. Random network graphs and noises are introduced to model the uncertainty and randomness in real-life networks. Network topology. Random network graphs are used to model the connectivity. The topology of network can significantly impact the performance of distributed averaging algorithms. The nodes The nodes are connected randomly based on certain probability distributions. Most of the changing of the network structures or measurement noises on distributed algorithms are calculated separately. In real networks, various kinds of uncertainties may coexist. For example, there may exist additive measurement noises and channel fading accompanied with random link changes. Many scholars have long been committed to developing distributed averaging algorithms with comprehensive uncertainties, establishing convergence conditions and quantitative relations between algorithm performances and network parameters. However, the theory of distributed averaging algorithm with all the random uncertainties mentioned above is still to be developed. The network topology model covers both cases with additive and multiplicative noises, different from the case with only multiplicative noises due to the introduction of time varying algorithm that gain to attenuate additive noises. The dynamic network associated with the algorithm becomes a time varying stochastic system. The exponential convergence of stochastic Lyapunov energy function, which is essential to obtain the almost sure consensus conditions, cannot be used. Besides, different from the case with only additive measurement noises, the network graph is assumed to be fixed, balanced, and strongly connected. In this way, the property of Laplacian matrix, the connected graph, can be directly used to get the contractive property of Lyapunov energy function. While this PPT studies the case of time-varying random graphs, and the network graph is neither connected nor balanced instantaneously, thus the method is not applicable. Noises in distributed computing. Noises are introduced to model the uncertainties and errors in distributed systems. Noises can be caused by communication delays, packet losses, or hardware failures. Dealing with noise is crucial to ensure the accuracy and convergence of distributed averaging algorithms. Consensus problem. Distributed averaging is a form of consensus problem where nodes aim to reach an agreement to the common value. Achieving consensus in presence of random network graphs and noises is a challenging task. Centralized averaging. A centralized averaging. A central node collects all the values from the network and computes the average. This approach is not scalable and may not be feasible in large-scale distributed systems. Distributed averaging with random network graphs and noises provide a decentralized alternative. Now, decentralized averaging. In decentralized averaging, each node will communicate with its neighbor nodes and updates its value based on received information. The goal is to iteratively converge and to average value through local interactions. Random network graphs and noises introduce additional challenges to the convergence process. Various consensus algorithms have been developed for distributed leveraging. Examples include the gossip algorithm, the push sum algorithm, and the diffusion algorithm. These algorithms leverage different communication strategies and update rules to achieve consensus. Gossip algorithm. The gossip algorithms involves randomly selecting neighbors to exchange information. Each node updates its value by averaging its own value with the received information from the neighbors. The process continues until all nodes converge to the average value. Push sum algorithm. The push sum algorithm assigns each node a weight and some value. Nodes iteratively update their weights and sum values based on the information received from neighbors. The average value is then computed by dividing the sum value by the weight. Diffusion algorithm. The diffusion algorithm uses a diffusion process to propagate information across the network. Each node updates its value by taking a weighted average of its value and received values from neighbors. The diffusion process continues until all nodes converge to the average value. Trade-offs and performance. Distributed averaging algorithms with random network graphs and noises involve trade-offs between convergence speed and robustness. Faster convergence often comes at a cost of increased sensitivity to noises and uncertainties. Performance evaluation and analysis are essential to understand the behavior and limitations of these algorithms. Robustness analysis. Robustness analysis studies the resilience of distributed averaging algorithms to randomly network graphs and noises. It explores the impact of different network topologies and noise models on the convergence performance. Robustness analysis help identify the conditions under which the algorithms can reliably compute the average. Convergence analysis. Convergence analysis focuses on studying the convergence behavior of distributed averaging algorithms. It investigates the rate of convergence and steady state error under various network topologies and noise conditions. Convergence analysis provides insights onto the performance guarantees and limitations of the algorithms. Applications and sensor networks. Distributed averaging with random network graphs and noises has application in sensor networks. Sensor nodes can collaborate to compute the average speed of sensor measurements. This enables applications like environmental monitoring and distributed surveillance. Application in distributed machine learning. Distributed averaging is also relevant in distributed machine learning scenarios. Multiple machines or nodes can collectively compute the average of their local model parameters. This facilitates collaborative training and aggregation of information in large-scale machine learning systems. Challenges and future directions. There are several challenges and open research directions in distributed averaging with network graphs and noises. Developing more robust algorithms that can handle various noise types and developing dynamics, investigating the impact of different noise models and network toppling on convergence, speed, and accuracy. Conclusion. Distributed averaging with random networks and noises is valued technique in distributed computing. It enables decentralized computation of averages in large-scale networks. Ongoing research aims to improve the robustness and performance of these algorithms. Thank you.